Mail and plus, sir.
Only
The message
48 are there.
message.
Only 48 are there.
Okay, sir. Done, sir.
இந்த ஸ்க்ரீனில் இருக்கு இல்லையா, இந்த ஸ்க்ரீனில் இருக்குது, நான் சைடில் இருப்பேன். Full screen PPT, is it visible, the full screen
Yes,
PPT?
Yes, sir. Yes, sir.
Yes, sir.
And I am standing the side, right? I am the
Yes,
side.
sir. Yes, sir. Yes. You can do, sir. But 1 minute, sir, please, sir.
No. I will wait for an instruction.
No instructions. Just you want to do this, sir. Introduction, sir.
I am before me. I have your HOD, Dr. Goindaraja,
Yes,
Yes, sir.
and Shobana, my student.
Yes.
Yes,
I am your kid, sir. How can I give instruction? We are coming from your hand, sir.
Thank you.
Sir, your university is opened. Are you going to your department nowadays?
Yeah, today the second day we went to the department. The second
Yes, sir.
day.
Yes, sir.
So no work, just like that, go and come.
Okay.
That's all.
Okay. So you planned for end semester, sir? Your university, they planned for end
Yesterday
semester?
there was a high-level meeting with the government side.
Okay.
I think they decided to conduct examination for final semester first, it seems. But what is the way, we don't know.
Okay.
But today,
Nothing is been said outside regarding.
today announced, sir.
Goindaraja,
Yes, sir.
Goindaraja is there.
Madan Raman. So the UGC has given a recommendation. All the deemed universities need to conduct final semester examinations.
So UGC today it will tell, tomorrow it will tell one more thing. But in
that's what-
reality, we have to wait and see what
sir.
is going to the situation this pandemic is. We don't know. Let us hope that the students should get benefit. That is important.
Yes, sir. In our university, they release the results of 6th semester, 8th semester, and BSc, MSc, all semesters results are released.
You print the mark sheet and give it to them by courier. That's all.
Once the results are over, now it is not possible to
Okay.
rethink again. It's not possible. We don't know what is the decision taken by our mandate.
If the students are there all around the country,
Yes,
it's
sir.
not possible to conduct. We'll see what will happen finally. This is all contradicting things happening.
Yes, sir. Yes, sir. And what about the next semester, sir? Are you planning for?
Nothing so far. We have not thought about that. HOD is not contacted us. The registrar has not told about that. But Arts and Science College, they are given the workload for Arts and Science College.
Yes, sir.
And they are ahead conducting
Yes, sir.
classes, online classes. Even we are ready, because we don't want to be idle without working.
Yes,
We
sir.
are ready at any time, but we are waiting for the instruction.
Yes, sir.
Fee collection is there. That is another headache is there.
It's another headache. Fee collection, another headache. And teaching mathematics through online is another big headache, sir.
Already people don't like max teachers. If you come on the screen, it will be a comedy piece for them. That's all. Kodandramadi is smiling. At least in the private institution, people listen. The government institution, they will enjoy.
Yes, sir.
That's what the effort you people are doing now. Somehow you are engaging your faculty members in online, and
Yes, sir.
this creates an interest
Yes, sir.
for people to, even we should do some classes in online. But only with the PPT, we cannot succeed, sir. We require blackboard and chalk.
Yes, sir. Yes, sir. Some modern tools, online tools.
But whatever it is, mathematics with the you have to play with the physically with the mind.
Yes, sir. But the concentration is very important.
Important. Practice is most important. You should see how students are practicing and discussing. With all this online, all show work. That's all. That's
Yes,
like
sir.
that. Go.
Yes, sir.
For us itself, it is not so easy.
Yes, sir.
The students, sir, that level we have to go down, and you should concentrate. Before us itself, you won't concentrate. When we are away, we don't know what is happening in their house, first of all.
Yes, sir.
Yeah. Now at least we are ready. Now closing the door, we are inside our bedroom and talking in webinar. So
And,
every
many
house will
students-
not have this situation.
Yes, sir. Many students have a connectivity problem. the storage problem, data usage problem. Many things are expected.
So psychologically, each and every family, in one way or other, some loss is there.
Yes,
Psychologically, that will affect the student psychology. That is first concept. Next, economical position. Then everything is there. Lastly, you have to come into our subject.
Yes, sir.
In spite of that, with the love, he will study. That's it. What else?
Okay.
The great effort you people are doing in this webinar.
Yes, sir. Yes, sir. Okay. Now it is 4 o'clock. So shall we start, sir? I will just give introduction, sir, about the thing. Babujee, everything is okay, Babujee? Babujee Pullepu?
Yes, sir.
Shall we start?
Yeah.
Okay. Good evening to all. I welcome all of you for this online faculty development program. I welcome all our faculty members who belong to our department. Also, faculty members belong to other department of Kattankulathur campus. Faculty members belong to other campuses like Vadapadi, Ramapuram, KTR. I welcome you all for this online faculty development program. I welcome the chief speaker, the resource person of the day, Dr. Baskar Babujee. I welcome you, sir, for your readily accepting and willingness to give the talk. We planned the talk just 2 days before. We planned on 2nd of July, and we asked our colleagues to fix the resource person. I'm very much thankful to you, sir, for accepting our notice in a short period, sir. I welcome all our department colleagues. Our management requested us to conduct an online series of webinars on the faculty development program for 10 days. 10 days duration for faculty members and research development program for research scholars. So we have planned our EFDP from 6th July to 16th July. Yesterday, Professor Angadesan started the first day, and today Professor Babujee is going to do it for the second day. And the series goes up to 16th of July. And from 17th onwards, we have research development program for our research scholars. So I am very happy that we are able to get good number of participants. Whoever is participating in the EFDP are going to give a e-certificate. And even though we are not able to meet in person, I'm very happy that we are meeting virtually. So I'm very happy that today we have day 2, and Professor Baskar Babujee, Madras University, Madras Institute of Technology, MIT Anna University, is going to deliver a lecture on applications of number theory in cryptography. I request Dr. Shobana to introduce the speaker to the audience. Dr. Shobana.
Hi, sir. So I'm happy and pleased to introduce my supervisor, Dr. J. Baskar Babujee, to present today's lecture. He received BSc, MSc and MPhil from Madras Christian College and PhD in graph theory from Jawaharlal Nehru Technological University, Hyderabad. Also received his postgraduate diploma in higher education in 2003 from Karnataka State Open University, Mysore. He has 210 publications in academic journals and international conference proceedings with totally 27 years of teaching experience, and currently as an associate professor in the Department of Mathematics, that is Division of Applied Science and Humanities, Madras Institute of Technology Campus, Anna University. He has guided 11 PhD scholars, 5 ongoing, 31 MPhil candidates, and 64 MSc projects. His current research interest includes graph theory, formal language and automata theory, number theory, cryptography, and geometric function theory. He has delivered 83 lectures in national, international conference, workshop, and seminar. He has also a lifetime membership in Indian Society for Technical Education, Academy of Discrete Mathematics and its Application, World Association for Scientific Research and Technical Innovation. Lectures delivered by Sir are always captivating and thought-provoking. Hope the same for these 2 hours. Over to HOD, sir.
Thank you for introducing the speaker. Now I request Professor Baskar Babujee to continue his talk. Sir, please, sir.
Thank you very much, sir. Let me first thank all the organizers, including the head of the department and Bapuji Pullepu for organizing this wonderful faculty development program for all your faculty members. Right. So let us all together pray the Almighty so that this dangerous corona COVID-19 should disappear from this world as early as possible and serve the humankind and all the creatures in the earth and the universe. So with that, let me start today our FDB section. So the idea today, what I'm having is to give a combination of pure as well as application. Anytime we are interested about knowing the application, we are always interested to know about the application. So let us also go in depth a little to the concepts, the fundamentals. So the idea is that when you are a owner of a car, you should know driving the car. When you're a driver of a car, you should know little mechanism of the system, your car. So when you apply a certain concept, that is a tool. Mathematics is a fundamental tool. So you should also know about that basic concepts. When you say numbers, it is in our blood. Number, everywhere number. So every individual has a number. So the analysis of a number is number theory concepts. So the beginning of research would have been from numbers, and there is no end for analysis, number theoretic, and the concepts and the hidden truth of numbers. Still, we are finding out the hidden truth of numbers. Various truths are coming out. So all these things are interesting in life. So when you have such a fundamental concept, numbers theory and properties, which is applicable everywhere, so then application becomes easy. So the idea is I have 4 PowerPoints today. So let me go with the 4 PowerPoints one by one. First, let me create some interest, taste on the concept, so that with the interesting idea, so that you will really like to go and learn fundamentals. And again, I come back to the application. Could you hear all of you?
Yes,
Is
yes.
it clear, audible? Okay, thank you. So let's go. Yes, okay, I'll continue. Fine, thank you. Number theory is a fundamental body for knowledge, just played a pivotal role in development of mathematics. Number 3 provides a fertile ground to professionals and amateurs. This screen is just, I want to take this, is hiding. Shall I move it? Shall I move it up? Is it okay? Fine. So although many of its results can be stated in a simple and elegant way, just some technical problem. Fine. Although many of its results can be stated in simple and elegant terms, their proofs are sometimes long and complicated. The statement looks very simple, proof looks complicated, but let us not get fear of it. Fine. The German mathematician Leopold Kronecker wrote, "God created the natural numbers, and all else is the work of man." Cryptology consists of cryptography and cryptanalysis, 2 components. One is cryptography, another one is cryptanalysis. The word cryptography is derived from the Greek word cryptos, means hidden, and graphen means to write. Cryptography is the art of science concealing the meaning of confidential communications from all except the intended recipients. Fine. Cryptanalysis deals with the breaking secret message. During the World War II, 30,000 people were engaged in cryptographic work. The breaking of the Japanese Purple Mission Code by the US cryptanalysis shortly before the attack of Pearl Harbor led to the Allied victory in the Pacific. Today, the US government and business employ tens of thousands of people and spend billions of dollars annually on cryptology. Fine. So, cryptanalysis deals with the breaking of secrets. The next slide, just a minute. Plain text. That's what the original message which we want to transmit or communicate, but in the secret form. Ciphertext is its a secret version. The key is the explicit formation of the cipher, so that the job of the cryptanalyst is to discover the key and then break the code. The process of converting the plain text to ciphertext is called encryption or encrypting process. And the device which does this job is called encryptor. The reverse process by the intent recipient knows the key and then he accomplished by decrypting. That's called decryptor. The encryptor and decryptor both may be algorithms to be executed by people or by computers. Thus, the method used by an unintended receiver to recover the original message is called cryptanalysis. So I want to keep it secret. I lock it and go. But the opponent person has to require the key to open it. Otherwise, he should prepare a key without breaking the lock. You have to open the door, open the lock. So he has to do the reverse process, closing, opening. So this is all like a game, right? How do you construct? How do you take it back? I give 5 rupees, I take it back 5 rupees. I multiply by 2, I divide by 2. The reverse process is required. So those days we used to go to house, some small kids used to be there. Then we say, okay, you think in your mind a number, 1 to 10, some number. Okay, the child will keep the number in their mind. Then you say that, okay, I'll find out the number. Please add 5 to it. Multiply by 2, subtract 2, then add 10 to it, and tell me what is the result. The child used to say the number, and then you just do the reverse process and then say, this is the number which you had in your mind. So this is a small way of tricky that what you have taken it, you've given it, you have to take it back. So a reverse process, anything you do it, you do the reverse process. So algebra also plays a major role in encryption. So you have the concept of semi-group, group, then you go for cyclic group, then slowly you go for ideal ring, and then field. So see, finally the field file. The field is a beautiful concept where you have multiplicative inverse, you have additive inverse. So when you put it, you have to take it back. So I hide the treasure inside the field, okay, and then I take it back after several years. Okay, his son, the grandfather would have kept inside treasure, and today it comes out, and it's a reverse process. So how secret you keep things in your house secure? I close the gate, then I close the first grill gate, then the single door, then inside bedroom, and then I have a bureau, then inside I have, so all in spite of this, the thief will come and take it and go. So that's what happening here. So how much you are doing the secret communication? How do you communicate secretly? Whether it be a password, or a PIN number, or any number. So how secure you're communicating? All these are of interest. Let us see one by one. The crypto system is a system for encrypting a plain text to ciphertext using a key. The cipher presents 5 crypto systems: affine, Hill, exponential, RSK, and NASCA based on modular arithmetic. There stands our modular arithmetic. The first 3 is convention and the last 2 are public key. So private key, public key. So how modular arithmetic, using modular arithmetic, how we are going to do this? Let us see by an example. So this is the flow chart or whatever it is. Plain text is taken and then it has to be converted to the encrypted to ciphertext. And then after that, the ciphertext encryption, the person will receive. And that fellow has to decrypt it and then find out the original plain text. So if you have a key, then do it directly. If you don't have the key, then the cryptanalyst comes and he finds out how to find the key. That's the case. Affine ciphers. In all crypto systems, we first translate each letter to a number. A conventional way of doing this is by numbering the letters. There are 26 alphabets in English. So English is the most easy language to study in the earth because other languages have plenty of alphabets. So it's only 26, so simple, easy. A to Z, the ordinal numbers is assigned. For A, 0, for B, 1, like that goes for Z, 25. So I'm employing 26 numbers, that is 0 to 25. Using this scheme, we translate the plain text into numeric message, which is then encrypted into a numeric ciphertext. Each number is then replaced by a letter. So that's what we are going to do. The recipient on the other side, the ciphertext, substitutes the ordinal number for each letter and uses the key. The key is the major thing here. Okay, the important thing. The numerical message by substitution letters vary numbers. Fine. So this is the number digits 0 to 25 in assigned as ordinal numbers to the alphabets letters A to Z, the English alphabets. Fine. Substitution cipher. We substitute a letter, the alphabet of each letter for the plain text. Caesar chambers. Around BC, 50 BC, 50 years before Christ, the Roman Emperor Julius Caesar, 100 to 44 BC, sent encoded message to his general Marcus. That is happened in 106 43 before Christ. During the Gallic Wars, using the substitution cipher based on modular arithmetic, think of the application. Think of the application of the modular arithmetic concept before Christ, how it has been used. That is the beauty here. Fine. The Caesar cipher shifts each letter by 3 places to the right. What is the meaning? A, B, C. A will shift 3 places to the right. That is, A will go to D. B will go to E. C will go to F. And like that it goes. So I'm shifting 3 positions to the right. Similar way, you have W go to Z and X goes to, it's a cycle. It's a cycle. W goes to Z, X goes to A, Y goes to B, and Z goes to C. So this is what by shifting 3 positions to the right. Very simple to make you understand the idea. So let P denote the ordinal number of a plain text letter, and C that the corresponding ciphertext letter. Look at the relationship with P and C. The Caesar cipher can be described by the congruence. C is congruent to P plus 3 mod 26. Whatever if I add, final result I have to take modulo 26. What is modulo 26? The remainder, the residue when you add P plus 3 right hand side and divide by 26, the residue, the remainder. The remainder is P plus 3 mod 26. Fine. Excuse. And this P and C lies between 0 and 25. Let us take an example. The encrypting message is "Have a nice day." Let me take this "Have a nice day" using Caesar key. Replacing each letter by its ordinal number. H stands for A, 7. A stands for 0th position. B is 21 and E is 4. Again, A is 0. So like this, I am taking from the table the ordinal number for each position, H, A, B, E, and I say nice day. Let me go and see the previous. Here you have A goes to D. Then this way, I pick up this ordinal number. Okay. So, have a nice day is replaced by the ordinal numbers like this. Now I apply the Caesar transformation. C is congruent to P plus 3 mod 26. So I'm adding 3 to it. Let's open this. So 7 becomes 10, 0 becomes 3, 21 becomes 24, 0 becomes 3, 24 becomes plus 3 is 27. But 27 modulo 26 is 1. The remainder is 1. Here, luckily that you see all the numbers are very safe here. The example which I have taken is like this.
Sir, it's one day.
Okay. So only one case I am crossing 26. But the other example I can give. So 24 plus 3 is 27. 27 modulo 6 is 0. So this is my, after transformation, applying the Caesar transformation. Fine. Substitute this letter to each ordinal number and group them in 5 in a block. So I am substituting the numbers The numbers are 10, 3, 24, 7, 3. Put 5 numbers in a block, 5 numbers in a block, and take back what is the corresponding letters of the numbers. So numbers and the resulting ciphertext message is KDYHD, QLFHG, DB. So nobody can understand what is this, provided if he knows that you have shifted the position 3, the right side, 3 positions in the alphabetics. And then he have to take back, once he knows the key is 3, then he will subtract that and go back reverse order, move left 3 position, and so it's very simple case. But the work is to make it complicated using number 3. That's what we are here today. So let us take the example, same example. Suppose the recipient receives this KDYHD, QLF, GDB. He will replace, he will start doing the work. Look at this, the ordinal number of KDYHD, 10, 3, 24, 7, 3, and DB, everything he'll find out. D is 3 and B is 1. Okay, now he has to do the reverse process. What is the reverse process? C equal to P plus 3. Now P equal to C minus 3. Earlier we had C equal to P plus 3 mod 26. Now we have P equal to C minus 3 mod 26. So retrieve the numerical plain text back. Go back and see 10 minus 3 is 7, 3 minus 3 is 0, 24 minus 3, 21, 0 minus 3, 0, 1 minus 3 is minus 2. But minus 2 is not valid. What is the equivalent of minus 2? 24. Minus 2 is congruent to plus 24 mod 26. So all the residues of 26 are 0 to 25. Minus 2 means add 26 to it, becomes 24. So this is now this. Let us go back and translate the numbers back in alphabetic format, which yields have a nice day. So I know the language English, so I'll break this here. A. I'll put have a nice day. D is break here. So 5 in a block is. So regrouping the letters, we recover the original message. Have a nice day. So we are going to have a nice day today. Fine. So this is how this sister cipher works out. It's a simple example. Now a question starts, how to complicate it. What number can we add to it? Is it enough? 3, 4, 5? No, we can add any k. 0 to 25, because it's a cycle. It's a cycle. You keep on adding 0 to 25, more than 25. The mod 26 will come back again to like a period. So totally P plus K will be under the control of modulo arithmetic 26. Okay, so there goes that. So this is another example with some value of K. This is the ciphertext. Okay, using P plus K, taking values. That is 7, and then it is been traced out back. This example. Let us never negotiate out of fear, but let us never fear to negotiate. The President Kennedy in our address. Fine. So the idea is to make you feel the flavor of what is encryption, what is text, and other things. Now, as I mentioned earlier, we want fundamentals before learning more and more applications. The questions in your mind is, what is this? Very simple. Okay, let me make complicated. I said about field. What is the benefit of field? You have multiplicative inverse. Okay, let me take a line y is equal to mx plus c. I give values of slope and then c, you get y is equal to mx straight line. Fine. I want to find x. What is x? X is equal to y minus c by m. So y minus c by m. So I want inverse, multiplicative inverse. So can I multiply your ordinal number and then add to it? Not only adding or subtracting, multiply and adding. A linear relationship. Inverse exists. That inverse should be an integer with 0 to 25. Fine. So if I do quadratic, if I do cubic, things get complicated. But inverse exists or not, that is the question. Any process if I apply Laplace transformation, I'll take Laplace inverse. When I apply Fourier transformation, I apply Fourier inverse. A simple system of equations, you take 3 equations, that's plain equations, 3 by 3 matrix, we are taking X equal to B. I am doing a transformation of 3 planes to a matrix system. So it has solution. Yes. When it, how to find solution? Find the Ax equal to B, X is equal to A inverse into B. So inverse again. Look at the inverse. So given a matrix, square matrix, I want inverse when I apply the matrix transformation. When I apply Fourier transformation to solve differential equation, okay, partial differential equation, whatever may be, inverse Fourier. When I apply Laplace transform, inverse. So similarly, inverse plays a major role. So what is the procedure to inverse? What is the system of equation? When does the equation has a solution? We're interested about solution, whether differential equation or ordinary equation. So that is another interest. Learn all these things and then go to depth concepts and then come to the concept of a RSA crypto system, which is really now fine. So what is a Diophantine equation? An equation with the two variables, maybe x plus b equal to c. That's called linear, okay, linear equation. And then you can find solution. It's a straight line. X plus b y equal to a straight line, not passing through origin, because it is, you know what is the case. It's y mx is passing through origin. So what is the solution? Infinite points are there in this straight line. Infinite points are in the straight line. But I am interested in only integer solutions. When I put x an integer, I want y to be an integer. When I put y an integer, I want x to be an integer. That is our interest. Go and see the Pythagoras theorem, right angle triangle. So that you say 3 square plus 4 square is 5 square. A square plus b square is c square. So ABC is the component. So I want integral parts. That's of interest. So solving the linear Diophantine equation, okay, such systematically involves Euclidean algorithm. You know what is Euclidean algorithm, how to use Euclidean algorithm. Okay, may not, you can refer the book later. Now don't worry about that. Fine. LDs, shortly said, linear Diophantine equation, were known in ancient China and India as applications to astronomy and riddles. So we begin our discussion with the interesting puzzles. So when you see here the word China and India together in my statement, now we are in the mode of boycotting all Chinese things. But what to do? Chinese and Indians in the ancient were good in mathematics. Okay. So let us start with the puzzle due to the Indian mathematician Mahavira in 850 AD. Fine. So let us see the puzzle. The puzzle is like this. I think you will enjoy this. If you know, okay, hear it again. 23 were travelers, 23 number, weary travelers entered the outskirts of a lush and a beautiful forest. They found 63 heaps. They found 63 heaps of plantains and 7 single fruits. And then they divide them equally, 23 shares. They found 63 equal heaps of plantains. Heap means, in Tamil we say sip. In each heap, maybe 12 or 13 or 14 will be there. Mostly it will be equal, not always. And 7 single fruits. Now I have to divide it equally. Find the number of fruits in each heap. So now we are going by example. See, mostly in the classroom, when you want to teach a concept, better handle it with an example. Any concept, property or definition, always the success of a teacher is to make the students understand simple way. Try to give example. With its own example, it's better. But see that it's always logically correct. That is most important. Otherwise, we become a joker. So try to give example. You have any statement, a theorem or statement. Before going to the proof, say outset of the theorem, where it has come, what is the necessity of it, and what is the essence of the statement. Try to make him, even you can work out with number and then prove it. No need of giving an open proof or abstract proof for him. Try to make him understand the statement, then he will try to understand the proof. So examples makes a teaching live. So in that way, this example is going like this. So I want to find out the number of fruits in each heap. There are 23 travelers. They want to equally take this. Okay, let x be the number of plantains in a heap. X be the number of plantains in a heap. That has to be found. Why not the number of plantains received by each traveler? So can we frame now equation? How many heaps are there? 63 heaps. in each heap X plantain. So totally 63 into X. Then 7 single fruits are left out. So that also we have to add. That gives me the total number of plantains. So Y is the number of plantains is by each traveler. There are 23 members. So 23 into Y is an equation. This is a linear equation. It's a straight line. Okay, it's a linear I want the Diophantine solution. This is a linear Diophantine equation. Why? Because I'm interested not in half or 1/2 or 3/4 shafts. I want integers. That is a great problem, right? When Lord Shiva was giving this one single mango to the two children, Ganapati and Subramaniam, Lord Muruga, there's a quarrel. So that in cinema you would have seen Thiruvalayadar. The Lord Muruga doesn't want to accept half and all. He wants full integer. So mathematicians also want a number, an integer. So we want integers, right? So infinite points are in a straight line, but we are not interested in those solutions. Any pair, real pair is a solution, but we are interested only integer pair, because how many plantains are there in each heap? How many plantains received by each traveler? So beautiful LD equation has been framed now. Since both X and Y must be positive, we are interested in finding only positive integer solution for the LD. Okay, solve it for Y. Fine, I bring it one side, 63x plus 7 by 23. Both X and Y are positive. What is the solution? So trial and error. Keep on giving values for 1, 2, 3, and so on for X until you get Y to be an integer. So if this has to be integer, this numerator 63x plus 7 should be a multiple of 23. All these things are there for us to think fine. But trial and error method, keep on substituting value for X. It comes out to be for 5. The nearest is close value to 0, 5. For X is equal to 5. Yes. X is equal to 5. Can I continue? Yes, any? Hello? Hello?
Sir, no problem, sir. You can continue, sir. There may be disturbance.
Thank you, Professor. X is equal to 5, then Y is equal to 14. This is the first solution which we can see. And again, if you keep trying, X is equal to 28, Y is equal to 76, another solution. In fact, there are infinitely many solutions. There are infinitely many solutions. But it takes time for do this by trial and error. But there is a procedure. We have results for that. Look at this is a table which has been tried. For X is equal to 14, Y equal. Then for X is equal to 28, we get 77. Fine. Let us come to the method, how to find solution after some time. Another ancient riddle called 100 Folds Puzzle, found by the mathematical classic book, the 6th century Chinese mathematician Chang Session. Example, let me see this, try to understand this example. Again, this example is also for another concept. If a cock is worth 5 coins, and hen 3 coins, and 3 chicks together 1 coin. See the combination. A single cock worth 5 coins, a single hen 3 coins, and 3 chicks together 1 coin. That is the combination. The question is how many cocks, hens, and chicks totally? Number 100. So you can have number of cocks, you have number of hens, number of chicks. Count all these 3. You get total 100 items. Can be brought for 100 coins. So you go to the market with 100 coins and see that these are the cost of cock, hen, and 3 chicks, 1 coin. So I have to purchase totally 100 numbers, all these 3 combinations. A beautiful problem. We can frame the problem and the equation. So the unknown things are cocks, hens, and Z the to be the chicks. Let us denote this by X, Y, Z. All are positive, greater than 0. Fine. So this way we frame the equation. X plus Y plus Z. Total number of items to be purchased is 100. First equation. Next, 5x plus 3y. What is 5x? Cost of 1 cock is 5. Then cost of 1 hen is 3. So 5 into x plus 3 into y. 3 cheeks cost 1 coin. So 1 into z by 3. That total cost is 100. So these are the two equations. This now how to two plane equations. Geometrically to say two plane equations. Okay, one variable x, so I can try to make it z is equal to 100 minus x minus y from equation 1, and then substitute in equation 2. Eliminate z from 1, substitute here. I get a new equation with the two variables. Now this looks like okay, two LDs is made a single LD. Of course, z is a relationship. Finally, 100 minus x minus y. So I made it a single equation. It's also a linear differential equation. Interest is to find the integer solution. So 7x plus 4y equal to 100. From this, I just substitution like 100 minus 7x by 4. Again, divide this 25 minus 7x by 4. So how to get integer solution? If I put x is equal to multiple of 4, x is multiple of 4, this ratio will go, I'll get an integer to some level, and then it becomes negative. Fine. So this is the analysis which we have now. So 7x by 4 must be an integer, but 4 does not divide 7. That's a problem. So x must be a multiple of 4. So when you say multiple of 4, x is equal to 4t. X is equal to 4t. Substitute that 4t, x is equal to 4t, 25 minus 7x by 4. It becomes now 25 minus 70. So the burden is reduced. Y is equal to 25 minus 70. Take this y, substitute here in z. You'll get z is equal to 75 plus 3t. X is equal to 4t, a relationship. Y is equal to 25 minus 70. Z is equal to 75 plus 3t. So t is arbitrary. So now start substituting 1, 2, 3 values for t and get the triple solutions. So that way we can do that and then find out the answer. So this is simple. The riddle of 4 possible solutions for t is equal to 0, 1, 2, 3. Okay. So after that, maybe go negative. So these are the positive possible solutions. These are the possibilities. Don't buy any cock, buy 25 hens and 75 chicks. Buy 4 cocks, 18 hens, 75 chicks. So this is the combination here. This is the combination. So this is the interest. Now, let us go into the concept. We are able to solve successfully the LDE, both the examples. There are 3 questions. Does every LDE has a solution? This is the question. So I draw a line, the graph sheet, straight line, ax plus by equal to c, or y is equal to mx plus c, whatever it is. X by a plus y by b equal to 1. All different types of straight lines. To draw a straight line, 2 point is enough for me. I draw a straight line. Randomly, I draw a straight line. The question comes now. There are infinite points on the straight line. Does all the solutions, all the points are integers? No, not at all. All the points are real, that we cannot say. The pairs, x and y, the solutions. But we are interested into integer solutions. That is the, if you take integers, the LDE has a solution. Does every LDE has a solution? Need not be. Need not be. Sometimes it may not touch integer point itself, the line, graph sheet. So next question. If not, under what condition does an LDE have a solution? That stands mathematics. Geometry is there. Number theory is going to come here. Geometrically, the problem is, do you have pair of integer points on the line? If not, under what condition? Yes, we can give condition. That stands mathematics. We can give condition. This condition, the LDE has a solution. For this condition is satisfied, it has no solution. That is there. If not, LDE is solvable. What is if not, LDE is solvable? Suppose the first case, what is the maximum number of solutions it can have? So, maximum number of solutions it can have. That is the question. See, you have infinite number of solutions, all real points, but we are interested only in integer points. So that's what main picture. The first question can be answered very easily. Consider this 2x plus 4y equal to 5, straight line, ax plus by equals 5. No matter what integer x and y are, but look at the left hand side, it's an even number. 2 into x is even number. Plus 4y, 4 into y is even number. Add even plus even, again even number, but right hand side is odd number. Definitely you won't get a solution, because how an even number will tally with odd number? So this LDE has no solution. So the first question answer, not every LDE has a solution. That is what we have answered with the first question. So like this, we can frame plenty of equations where the LDE is, which has no solution. Simple, very simple it is. At the outset, problem looks very difficult, but if you analyze, so simple. That is the beauty of the number theory. Next, we establish the necessary conditions, the sufficient conditions for LDE to be solvable. In fact, the proof provides a formula for the arbitrary solutions solved. I am not going to detail of the proof. I'll just show you what is what. And Indian mathematician Aryabhatta provided a complete solution for the LDE of two variables. A portion of the proof of the theorem 1, which is long but fairly straightforward by this method. Let us see. This is the theorem. LDE ax plus by equal to c is solvable if and only if the GCD of this coefficient, that is a and b, coefficient of x, coefficient of y, a and b, you take that the greatest common divisor is d is the greatest common divisor. If that greatest common divisor d divides this right hand side c, then you have solvable, you have solution. How many solutions are there is the next question. First, whether it has solution or not. Look at the previous case. The previous case was different, 2 and 4. The previous case, can you apply this? Immediately can you apply and see what happened? Yes, what is the GCD of this 2 and 4? 2 is the greatest common divisor, 2 and 4. 2 does not divide 5. That ends the matter. Outside itself, the answer is right, but apply this tool and see. Yes. So let me take one solution. Any trial method called particular solution or initial solution, whatever it is. And then we can generate plenty of solutions. That is what here given. I will skip the proof. I don't want to go to proof. X is equal to x naught, the particular point, plus b by a. B is this coefficient, a is this coefficient, into t, and y is equal to y naught minus a by d into t. What is d? D is the GCD of a and b. D is GCD of a and b. So t is arbitrary integer. So the proof goes, beautiful proof we can enjoy. If you see the proof, you will really like the proof. So sometimes you see the proof techniques of congruence relationship and all comes by induction hypothesis. Some see the major difference, the proof techniques in algebra, proof techniques in analysis. Analysis, there will be a flow. Algebra, there will be a construction. So some things required previously. With that, certain proofs have constructive proofs. An analysis from the concept they go. That's the beauty of analysis. Both has its beauty. Both has its duty, involvement. Number theory, miracle proofs are there. Practically, we take something and bring the proof. That type of proof I have in Euler's theorem, one theorem. That is going to come in our talk itself. So sometimes in our research group in Anna University with my students, when we worked out with some chemical compounds, molecules, some topological index, we got beautiful results that gave us beautiful congruence relations. That is not the talk today for me, but still, when you do a certain job, we aim for a output, but you get plenty of different type of outputs. That is the beauty of mathematics here. Especially when you do a calculation and go, some in-between results are coming. That is the beauty I want to say. Fine. So here, let us see. There are 4 parts of the proof. First, we should say it is solvable. We require some basic concept for this. So today, I am not going to do all those basics. So I'll skip the proof. So this is the idea: x naught plus b by d to t, y is equal to y naught minus a by d. It's a solution of the LDE. Okay, the solution is of the form. Fine. So that is the proof. Then uniqueness of the proof. All these things goes. So, and then the general solution is what we said earlier. Fine. Right. Suppose the coefficients of that is a and b, okay, the GCD is 1. It is again solvable because 1 divides the c. 1 is the number which divides any number, non-zero number. Solvable. The general solution is simply that d is 1. So x naught plus b by d y0 minus a by d is 1. So answer is direct like this. It's x0 y0 is a particular solution, and almost it has a unique solution. That is also another case. Fine. Now a problem just like that to enjoy. 3 LDs are given. Determine whether the LD has a solution. Yes. The first one, the GCD is 6. 6 divides 12 and 18. GCD is 6. 6 divides 30. So LD has a solution. Second one, GCD is 1. So this 1 divides, so it's, by the corollary it has a unique solution. And third one, 6 and 8, GCD is 2, does not divide 25, as not solvable, as no solution. Come back to the Mahavira puzzle now. We started this section, second PPT, with the Mahavira puzzle. What was the Mahavira puzzle? There are 23 travelers, okay, traveling in a forest. They saw 63 heap of fruits and 7 fruits, single fruits. Totally, the equation was framed like this: 63x plus 7 equal to 23y. We have shifted this to the left and right side. We have made it as an LDE. Mahavira puzzle, trial and error answer we sought. Now we are going to apply this linear Diophantine equation concept. So that is brought into this form: ax plus by equal to c. Now take this a and b, the GCD of 63 and the number 23 is 1. So it has a solution. To find the particular solution, we express the GCD 1 as a linear combination of 63 and 23. GCD is 1. This is Euler Euclidean algorithm. Euclidean algorithm, how to find the GCD. Yes, GCD is found. Once you find the GCD, can I express the GCD as a linear combination of 63 and 23? So this is a separate Euclidean algorithm we can apply. Maybe I can quickly tell this. 63 is written as 2 into 23 plus remainder. Take this Euclidean algorithm. I'm explaining Euclidean algorithm quickly for you. 23 is equal to 1 into 17 plus 6. And 17 is 2 into 6 plus 5. And this 6 is equal to 1 into 5 plus 1. And this 5 is 1 into 5 plus 0. The remainder is 0. What is the GCD? GCD is the last non-zero remainder. Last non-zero remainder is the GCD of 63 and 23. Take that, go back, reverse process, the reverse order. So look at 1 is equal to 6 minus 1 into 5. 6 minus 1 into 5. Okay, take this 5. 6 is equal to 17 minus 2 into 6. Look at this. 6 is equal, this is 17 minus 5. Okay, I substitute. Okay, fine. This is what it goes. So likewise, do the reverse process. Finally, end up with minus 4 into 63 plus 11 into 23 is 1. I'm able to express the GCD of 63 and 23 as a linear combination of themselves. Beautiful theorem is there. You would take a fundamental theorem before entering what is the. Let's close it. This result stands basic result expressing the GCD of two numbers as a linear combination of themselves. Any number theory book you can find. Well, multiply both sides of the equation by minus 7, because right hand side I had minus 7. I do that to the LD, then I get like this: 63 into minus 7 into minus 4, 23 into 11. So I am getting 63 into 28, 23 into 77. It shows that this x0 is this one solution, y0 is equal to 77 is another solution. So I didn't get that minimum solution. I got a solution. Okay. So the solution is like this. Now look at this, our LD general solution. Substitute here, x is equal to x0 plus bt, y is equal to y0, b by d into t, a by d into t. So we get this. From that, for various values of t, you get many solutions. Fine. Another one puzzle. With that, we can go ourselves to next concept. October 9th, 1926, Saturday Evening Post carried a fascinating puzzle by Ben Amis Williams titled Coconuts. It concerned a building contractor desperate to prevent a tough competitor from giving. Okay, I'll read the problem. Fine. This is the problem. look at the problem. It's very big, but interesting. So how this goes? 5 sailors and a monkey are marooned on a desert island. During a sunny day, they gathered coconuts for food. 5 sailors and a monkey along with them. Okay, they gathered the daytime some coconuts for the food. So totally 5 sailors, 1 monkey, 6 people are there. They decided to divide them in the morning the next day, and they took a rest in the night. So they decided to divide them next morning, and they took sleep. What happens? When all the people are sleeping, one fellow got up, one sailor got up. Other 4 people are sleeping. Monkey is also there. One sailor gets up and divides them into 5 equal piles, 5 portions. When he divides into 5 equal piles, one is left out, one coconut is left out. What he does is he throws it to monkey. The monkey eats it, there ends the matter. He hides his share. That is the beauty here. He hides his share, puts the remaining coconuts together, and goes back to sleep. So one sailor gets up, divides into 5 piles. He gets one balance left out, throws to the monkey. The monkey eats it. He mixes all these 4 shares and put it in the corn. Goes to sleep. After some time, the second sailor gets up, divide the pile into 5 shares. He again gets one coconut left out. He puts to the monkey again, and then he puts he takes its share, hides it, combines other things. He goes to sleep. One by one, all the people are doing like this. Next day morning, they divide the pile equally among them. Again, they find that one coconut is left out. So next day morning, all of them sit together, all the 5 people in the monkey. They make it to 5 shares. They still find one remainder. They throw it to monkey. Find the smallest possible number of coconuts in the original pile. Many solutions are there, but we want the smallest solution, the minimum number of coconuts which is possible. Divide by 5, remainder 1. Divide by 5, remainder 1. But what is the original? Original is what is left out. When one fellow hides his share, the left out is the original for the second calculation. So how is this possible? We know the number of coconuts, the original pile n. Then let u be wxy denote the number of coconuts each sailor took after each division. So how many times division would have happened? 6 times, because 5 times 5 people did without knowing other people's knowledge, and once they sat and did with all others' knowledge. And z be the number of coconuts each received after final division. So this is how the equation is framed. We have originally n coconuts. A person divides into 5, he gets one balance. The equation is 5u plus 1. So it is not divisible by 5. The number is not divisible by 5 because I get a balance 1. Okay, he takes one share u, and rest 4u is there. 1u he takes, 4u he throws it, puts together, and he sleeps. Now this second fellow will get up, and this 4u will be divided to 5 parts, say 5v, balance 1 throw to monkey. He lies down. The next person, does he hides 1v, so balance is 4v. This 4v is divided into 5w, third person, and then 1 is thrown to monkey. 4w is left out. Another person gets up, he divides it to 5 parts, 5x, 1 left out. The last, this fellow comes 4x, divides into 5, balance 1. So 1, 2, 3, 4, 5. Next day morning, left out is 4y. All the 5 people will take 5z, balance 1. So this is the equation now. How to solve this? How many variables are there? Plenty of variables are there. How to solve this? These equations yield an LDA, a single LDA. Look at this. What is happening here is I am just doing substitution. That's all. Framing equation is there. I substitute z here. For y, I put 5z plus 1. For X, I substitute. For W, I substitute. For V, I substitute. For U, I substitute. Now, finally, I have the relation for the two variables. The last variable Z and the initial variable N. So, number of coconuts. So, I get a linear Diophantine equation. Why it is linear? I want a linear solution. I want a integer solution. That's why I'm telling that I have to see whether it's a Diophantine or not. You know the condition that Diophantine equation set of Diophantine is solvable or not solvable. I am interested only integer solutions. That's why I'm using Diophantine. It's a linear, so linear Diophantine equation. Now it's our job to find whether solution exists, and then if solution exists, find out the solution. So 15,625 Z minus 1,024 N is minus 11,529. So let us take these two variables Z and N and then see the GCD of the A and B. It comes out to be 1. GCD is greatest common divisor is 1. So again, use the Euler's algorithm and trace out the linear combination. Find out Z and N, the linear combination, how you split this GCD into combination of the A and B itself. The procedure, same procedure by Euclid algorithm, the reverse processor, and then you get it the solution to be like this. This is a negative number, here also negative number. Fine. Okay. So this looks to be very big negative numbers. Now we can put it in the form for Z and for N, and then apply the arbitrary integers, T to be your arbitrary integer, and supply it, and then try to get the smallest positive number. Okay, the smallest positive number when you try out this in calculation. The original pile would have 15,621 coconuts. If you do this number 15,621, every time you divide by 5, you get a residue 1. The balance one part residue is going to be 1. Residue means remainder. Fine. So now, before going to modular arithmetic or our congruence, these again the basic concept. These are the tools now for us to study our RSA system and other things. Congruence modulo M. So let us understand what is congruence modulo M. M is a positive integer, then an integer A is congruent to integer B modulo M if M divides A minus B. We simply write A is congruent to B mod M. M is the modulus of the congruence relation. So when I divide A by M, the remainder is B. Or if I take this B here, left hand side, A minus B is congruent to 0 mod M. That means what? M exactly divides without any remainder. M is dividing A minus B, or A minus B is divisible by M. M divides completely A minus B. So A minus B is 0 mod M, or A is congruent to B mod M. If A is not congruent to B mod M, we just put a slash, that's all. Okay, see an example. Always example is important. 5 divides 23 minus 3. That is 23 minus 3 is 20. So I can write 23 is congruent to 3 mod 5. Similarly, 48 is congruent to 12 mod 6. Of course, I have properties. I can divide through by 2 or 6, whatever it is. Slowly we'll go to that. 28 is congruent to minus 4 mod 16, because if you bring it here, it's 32. 32 is 0 mod 6. So I can add, I can subtract up to, I can reduce further using modulo 16. The remainder is 0 to 15. Okay, 28, when you divide by 16, the remainder is 4. Minus 4, minus 4. Minus 4 is nothing but if you want to positive, add 16 is 12. So 16 plus 12 is 28. 16 plus 12 is 28. So minus 4, I don't want means I can add 16 to it. If I add 16 to it, becomes 12. 28 is congruent to 12 mod 16. But 20 is not congruent to 3 mod 4. Yes, of course, 4, 5 is 20. It exactly divides. 3 is not possible. Bring it 3 here, 17. 17 is not congruent to 0 mod 4. So because 4 does not divide 17. Likewise, 18 is not congruent to minus 6 mod 4. Likewise, fine. We use congruences in everyday life, often without realizing it. We use congruence modulo 12 to tell the time of the day. Congruence modulo 7 to say day of the week. Okay, so what is the 7th day? The 7th day. What is the when you keep on add 15 to it? Okay, take divide by 7. Okay, 8th day. First is Sunday. 8th is Sunday. Then again 8 plus 7, 15 is Sunday. If Monday, if Tuesday is 4th, 4 plus 7, 11 is next Tuesday. So this is the repetition here. The odometers of automobiles use 10 lakhs as a modulus. So on. Fine. Spouse. So next, I'm sorry, just a minute. The following result is simple but very useful for us. Look at this result. A very simple result. A is congruent to B mod. If and only if A is equal to B plus Km. Very simple. Very simple. When I divide A by M, okay, I get remainder B. I get remainder B. Or this A minus B is a multiple of M. M divides A minus B. M divides A minus B. Because A minus B is 0 mod M. When M divides A minus B, M divides A minus B. A minus B is a multiple of M. How much times? Some integer times K times. So A minus B is equal to Km. A minus B equal to Km. Therefore, A is equal to K plus B plus K. A is equal to B plus K. So that's the proof here. So nothing to worry. This is a useful result. And we have examples for this. Fine. I'm skipping this. Then the usual congruence relationship is reflexive, symmetric, and transitive property. A is congruent to B modem, B is congruent to C modem, then your usual transitive property A is congruent to C modem. I take this proof for this. This is I don't require because we are not going a coursework in number theory. I want to give you all the basic flavors and then enter into the main content. So certain things I'll skip here, not necessary. Whichever requires, I will go through. Every integer is congruent to exactly one of the least residues 0, 1, 2, 3 up to m minus 1 model. Look at this corollary. What is modulo m? What are the numbers in modulo class m? 0, 1, 2, 3 up to m minus 1. These are the possible remainders when I divide a number by m. That is the corollary here. Every integer is congruent to at least one of the least residues. The remainders, the residues. What are the residues for modulo m? 0 to m minus 1. So any integer if you take, definitely one of these will be the residue. No doubt in it. Fine. So some examples. Here I will skip this. I want only the result. Complete set of residue modulo m. Another interesting. Take this now, set integers, a set of integers set to be a complete set of residue modulo m. Idea is if every integer is congruent modulo m to exactly one of them. To understand this, look at this set of integers a1, a2 up to am. When do we say this is a complete set of residues modulo m? If they are congruent to modulo m to at least a 0 or 1, 2, 3 up to m minus 1 in some order. In some order. See, that is what is say, the order may be varying. But somehow these are the residues. If I take m numbers, that m numbers, when you apply modulo for m numbers, a1, a2, am, definitely the residues will be one among this number 0 to minus 1. Look at the example, always it will be very clear. I have here 4 numbers, minus 12, 9, 6, 23. Is a complete set of residue modulo 4. Because there are 4 numbers, I take modulo 4. There are k numbers, I take modulo k. This is the relation, beauty here. When I take modulo 4 for all the numbers, first number, minus 12 is 0 mod m, 9 is equal to 1 mod 4, 6 is 2 mod 4, 23 gives me 3 mod 4. The remainder is 3. So what are the remainders here? 0, 1, 2, 3. These are the 4 residues for modulo 4. But they may be in some order. Even if I put this in the second, I put 6, then minus 12, then 23, then 9. These are the residues. That's what the statement says. Very, very useful for us in future. Okay. So look at here some properties. A is congruent to B modem, then C is congruent to D modem. Just add a left-hand side, right-hand side, right-hand side, right-hand side. Multiply left-hand side, right-hand side, right-hand side. These are beautiful properties. I'm not going to go to adding two congruence relation, multiplying congruent relation, left side and left side, right side and right side. Fine. So what I require, I'll explain. Others I'll skip. So this proof is we can say any standard textbooks and an example for this. Okay, to maybe this is also a very interesting questions. I'll skip all these things, the regular problems in number theory, its application, so on. Fine. Certain slides which I don't require, I'm skipping those slides because not necessary for us. We can understand without this. And again, the properties here, A is congruent to B mod C. C is an integer. Then I can add the C to both the sides. I can subtract C on both sides and multiply C on both sides. Look at the three properties: A plus C, B plus C, A minus C, B minus C, A into C, B into C. All is holding good. The last one is when I square both sides, also it's true. A square is congruent to B square modem. Not only this, A power K is congruent to B power K modem. So that's given by an example. So these are the beauty. Look at the generalized theorem. If A is congruent to B modem, then A power n is congruent to B power n modem for any positive integer n. The proof is by weak induction. Okay, this result will be useful for us in our next PowerPoint sections. Okay, again, a few problems which I don't want to deal. So this is one application of what we've seen. Find the remainder when 16 power 53 is divided by 7. Is it possible to go quickly once you know the properties? Then it's fine. But we have, apart from this solution here, we have other techniques also in coming as PowerPoints. What is the remainder when 16 power 53 is divided by 7? Now reduce the base is the problem. Base is 16. Okay, can you reduce this base? Yes, it's possible by the property. 16 is 2 into 7 plus 2. So 16 is congruent to 2 mod 7. The remainder is 2. By the previous theorem, okay, 16 power 53, I can reduce as 2 power 53. So this is one beautiful result. 16 power 53 is 2 power 53 because I'm replacing 16. 16 is equal to 2 for me in modulo 7. 2 is same as 16 for me because modulo class 7, numbers are from 0 to 7. So 16 goes to the class 2. So 16 becomes 2 here. Now express the suitable powers of 2 congruent modulo 7. So again, what it is, 2 power 3, you know very well, 8. 8 is 1 mod 7. 2 power 3 is 1 mod. So how many 2 power 3 are here? In 2 power 53, how many 2 power 3 are there? 17 2 power 3s are there. So 53 is written as 3 into 17 plus 2. So 2 power 3 power 7 into 2 square. So all this will go to 1 power 17. 1 becomes 1 here. 2 square becomes 4. The balance 4 is smaller than 7. So further I did not go here. So 4 is the remainder. So for the answer for the question is 4. So this is how the trick goes in number theory. Fine. Again, we have another question. Remainder of 3 power 24 divided by 17. 17 is a prime number. Even previous case was a prime number. Let me tell this then. So this I am skipping. So modular exponential. I'm raising to the power. What happens? So on. So again, I'll skip all these things for me, not necessary right now. This is another interesting problem. Fine. All these things I'll skip. Fine. Now we are in a equation, congruence equation, congruence relation, linear congruence. Ax is congruent to B modem. Is solvable. See, earlier in the beginning of this PowerPoint section, we talked about LDE, linear Diophantine equation. Fine. Now this is linear congruence. What is linear congruence? Instead of equation, I put a congruence list. Ax is congruent to B modem. Ax is congruent to B modem. Is it solvable? Yes, it's solvable if and only if this GCD of A and B divides A and M. D is GCD of A and M. If it divides the right hand side B, it has a solution. Okay. Then if it is If D divides B, it has solution and it has a D incongruent solutions. So this is a linear congruence equivalent to, okay, how do you convert the congruence relation equation, an ordinary LD, linear differential equation? Look at this. AX is congruent to B mod M. What is the meaning? M divides AX minus B. M divides AX minus B. So AX minus B is divisible by M. So AX minus B is equal to some constant times M. So equal to My. So I push this My left side, I push the B right side. So I frame an LD. AX minus B is divisible by M. So AX minus B is equal to, I remove this congruent, put equal to M into Y. So AX minus My is equal to B. So now the problem is reduced to solvable from congruence to solvable LDE. When is LDE solvable? When D divides B. D is nothing but, what is this? D is nothing but the GCD of A and M. So that proof now here it's valid here. So this is the result. So again, the result looks like here. There you used to put what you say B and A. Here I'm putting M and A. That is the difference here. Solution. Infinite solutions. We can pick up the congruent solutions for the value of T. Okay. So this way it goes, and again it has a unique solution if GCD is 1. Look at the problem. Determine if congruences X, 8x is congruent to 10 mod 6, 2x is congruent to 3 mod 4, 4x is congruent to 5 are solvable. Find the incongruent solutions when the congruence is solvable. Look at the first one, 8 and 6. The GCD is 2. 2 divides 10. Yes, 2 divides 10. So it is this has a solution. So the congruence 8x is congruent to 10 mod 6 is solvable. It has 2 incongruent solutions. 2 divides the right side. 2 divides 10. 2 is GCD of 8 and 6. 2 divides 10. Fine. The second case is that 2 and 4, 2 does not divide 3. 2 does not divide 3. Therefore has no solution. The last one, 4x is congruent to 7 mod 5. GCD of 4 and 5 is 1. And 1 divides 4. GCD is 1. Therefore it is a unique solution model of 5. That's way. Well, so another technique is you can take it here. This problem is 12 and 18, 6 divides 48. There are 6 incongruent solutions. 6 solutions are possible. What are the 6 solutions? I put the particular solution to be x naught, and then I work out, okay, they work out this for various values of t, 0 to 6 here, because modulo 6. Okay, but telling that x naught is 1. The rest of the solutions we can frame with the 1 plus 3t, 1, 4, 7, 10, 13, 16. Starting values of t is equal to 0 is 1, t equal to 1, t equal to 2, t equal to 3, t equal to 4, t equal to 5. Not t equal to not 6, t equal to 5. 15 plus 1, 6. So these are the 6 incongruent solutions. Not only that, we can reduce the equation. See, we can reduce the equation like this. It was 12x congruent to 48 mod 18. I can reduce as 2x congruent to 8 mod 3. This is also possible. We can divide congruence by 6, throughout division by 6. And I get x is congruent to 1 mod 3. Still, again, it is 1 plus 3t. So I get the various solutions. Okay, now go back to Mahavit's puzzle. The 23 travelers in a lush, beautiful forest, getting 63 heap of fruits, 7 single. So that we had an LDE. Now, can you convert this into congruence? Look at this beauty of, see, we framed equation, we solved a trial and error, then we found the LDE procedure, we interpreted as an LDE, we got a solution. Now we are learning congruence. Congruence we converted to LDE in the previous case. Now LDE is converted to congruence relation. So the congruence is 63x is congruent to minus 7 mod 23, or 23y is congruent to minus 1 mod 63. If I divide by 23 modulo 23, apply mod 23, 63x plus 7 are congruent to 0 mod 23. Or I will put 63 is congruent to minus 7. Okay, minus 7 mod 23. Or other way, divide by 36, 63, mod 63. So we have 2 linear congruences. Again, the first one yields we take this and then we check this AX congruent to B modem, the procedure. And for this, what we require to be able to finely tune this 4 into 6. This is a property again, multiply by 4 both sides. Earlier we had 4 properties, right? Adding C, subtracting C, multiplying C, squaring or power n. So I'm using that property 6 into 4, then 7 into 4. So the both sides by 4. So this gives me comfortably 24. 24 mod 23 is 1. Balance is x here. 28 mod 23 is 5. X is equal to 5 is the solution. Not only that, 5 plus 23t. X is congruent to 5 means x minus 5 is multiplied by 23. So constant times 23, some t into 23. So x is equal to 5 plus 23t. X is equal to 5 plus 23t. This will yield for me a general solution. So this is how we can go front and back. LD to then second equation, LD has been solved, 14 plus 63t. Then this is another modular inverse concept. We can take the idea of invertible inverse. Now we come to the concept here. Find the inverse of multiplicative inverse of 5, 1 by 5. Find the additive inverse of 5, minus 5. But in modulo, what is the inverse? That is the beautiful question. In modulo arithmetic, what is inverse? To take the linear congruence, X is congruent to 1 mod m as unique solution if and only the GCD divides 1. Okay, this is 1 already, so an divides 1. Unique residue X. This is said to be invertible and X is said to be inverse of modulo m. Write as A inverse. What is the meaning of inverse? X inverse of A is A inverse. Multiply A into A inverse, answer should be identity 1. So A inverse is 1 here. So usually A into A inverse is 1. So if this inverse is equal to itself, is called self-invertible. That's called self-invertible. So the idea of inverse, self-invertible. Same. Look at the example. 7 into 8 is congruent to 1 mod 11. Yeah, of course. What is this idea? 7 8 56. 56 divided by 11. 5 11 is 55 plus 1. So the residue is 1. So 56 is. So here I am writing 56 as 7 into 8. What happened is if I take A equal to 7, A inverse is 8. So 7 is invertible. Inverse of 7 is 8. 8 is invertible. Inverse of 8 is 7. Under modulo 11. So that is 7 inverse is 8 and 8 inverse is 7. So that we have to keep in our mind to go further. So inverse exists, additive inverse exists, multiplicative inverse, field is there in algebra. Here for modular arithmetic, inverse rise. Look at this beautiful. 10 has its own inverse modulo 11 because 10 into 10 is 100. 100 is 1 modulo 11. 100 is 1 modulo 11. So the self-invertible 10 is called self-invertible. Again, there is a catch here for us. Inverse are useful in solving linear congruences. To this, we return the congruence X would be GCD of A and B is called A and M is 1, then has inverse A inverse modulo M. So look at this play here. I am multiplying using the concept multiplying both sides. I take the inverse itself and multiply both, pre-multiply A inverse X, A inverse B. What happens? A inverse is A is 1, here A inverse B. So X is equal to A inverse B. So like X is equal to A inverse B in your matrix, like any linear relationship, the X, the solution for the linear congruence, X is congruent to B mod M is very simple. X is equal to, from this relation, pre-multiply by inverse. So X is equal to A inverse B mod M. So this is the solution for this linear congruence equation. So the unique solution for this exists. Okay, then the least residue of A inverse mod B. So we have this cock example. You can say I am in a meeting. So you can speak to her after some time. If the cock worth 5 constants, go to that problem. Earlier we had the second one after Mahavira puzzle, right? So for that problem, let us take the same story. X, Y, Z stands for cock, hen, and chicks. You remember the equation 1 and equation 2. It was standing. So eliminating Z, we got this 7x plus 4y equal to 100. And then I can yield this 7 is congruent to 4 mod 4. I can make this, look at this, 7x plus 4y equal to 100. That is, we made 7x is equal to 100 mod 4. 3x is equal to 0 mod 4. I'm dividing by 4. Okay, I'm dividing by 4. So I can prepare this congruence equation and then easily give this solution for this. So that is the beauty here. I can go for the general solution and so on. That is the beauty here. Okay. Okay. Now, system of equations. Similarly, system of linear congruences. See, one by one, the concept is growing slowly now. Here is the catch now, where we're going to see Chinese remainder theorem. System of linear congruences. What is system of set of equations? Okay. That is the Chinese remainder theorem. Do you have a solution for this? Yes. Look at the problem. Find the number that leaves a remainder 1 we divide by 3, remainder 2 when we divide by 5, a remainder 3 when we divide by 7. So can you find out what is the value of x? Yes, we can write this as a congruence language. The riddle is to find the integer x such that when you divide x by 3, remainder is 1. When you divide x by 5, remainder is 2. When you divide x by 7, remainder is 3. So I am framing 3, a set of congruence equations. X is congruent to 1 mod 5, x is congruent to 2 mod 5, x is congruent to 3 mod 7. So this was solved, and then this is called the Chinese remainder theorem. The solution for this is the Chinese riddle. Okay, so that the Sun 2 puzzle earlier, x is equal to 1 mod 3, x is equal to congruent to 2 mod 5. So this is a lengthy proof. I'm not going to go to the proof of this. The procedure is there. As per the procedure, we find out the solutions. It's the smallest solution is 52. 52 is the number, unique solution. Okay, under by the Chinese remainder theorem. Okay, we find the solution for this. So the theorem states like this: you have a system of congruent solution. X is congruent to A mod MA. How many equations are there? K equations are there. Pairwise, they are relatively prime. All the moduli pairwise, and it has a solution. The procedure is a lengthy one. We don't require at this point. Just to say, I'm telling you, Chinese remainder theorem is solving system of congruence equation. Procedure is there. We can do, no problem. So let us go into the next idea which we require. Well, so this with this I will go to my third what do you say, PowerPoint. I have 4 PowerPoints, as I said earlier. Now I am going to the third PowerPoint. Without this, I cannot go into the fourth. You cannot understand the 3 classical milestones. So beautiful results: Wilson's theorem, Fermat's theorem, and Euler's theorem. When I put all these things for you, then I can further go into the concept. So such a significant role in the theory of congruences. Okay, these 3 theorems called classical results. Again, I as I mentioned earlier, go with examples. Even if you have a result, try to not go to the proof immediately for the students. Try with example. Apply the theorem on numbers. Apply some numbers. Check it. See, already it is proved. We are checking means we are enjoying the result by examples. Some proofs are like that. Look at this lemma. A positive integer A is self-invertible modulo P if and only if A is plus or minus mod P. P is not think the prime number. It is given notation P. Modulo class P. What are the residues modulo class P? 0 to P minus 1. Self-invertible. A is self-invertible is what? A into A inverse is 1. That's called inverse property. Self-invertible means A equal to A inverse. The element inverse is itself. When it is possible, only if it is congruent to plus or minus mod P. Only this proof I will tell, and later proofs I can skip. Suppose A is self-invertible, A into A inverse is 1. That means A is equal to A inverse, self-invertible. So A square equal to 1. So there we are framing a congruence equation. So what is the meaning of A square congruent to 1 mod P? A square minus 1 is divisible by P, or P divides A square minus 1. P divides A square minus 1. That means P divides A minus 1 into A plus 1. That means P divides A minus 1 or A plus 1. A number divides the product of two numbers. A number divides the product of two numbers, means either divide A or B. A minus 1, A plus. So R comes here. So when P divides A minus 1, I am framing the congruence A is equal to 1 mod P. When P divides A plus 1, I am framing a congruence A is congruent to minus 1 mod P. Conversely, if A is 1 mod P or minus P, then by property, A into A square, 1 into minus 1, okay, whole square, A square, A square, A square, whole square. This is going to be 1 mod P, self-invertible. Fine. By this lemma, there are exactly two least reduced modulus P that are self-invertible. What are the two least reduced modulo P which are self-invertible? 1 and P minus 1. 1 is self-invertible, P minus 1 is also self-invertible. The congruence x square is congruent to x square is congruent to 1 mod P has exactly two solutions, 1 and P minus 1. For example, the self-invertible residues modulo 13 is equal to 1 and 12. So 1 square is 1 mod 13 and 12 square is 1 mod 13. That you can verify. So the example, take the prime number P is equal to 13, modulo 13, 1 and 12. So 1 square is equal to 1 mod 13, 12 square is 1 mod 13. In other words, I can frame that x square is congruent to 1 mod 13 or 1 and 12 or modulo 13. Fine. Take an example, P equal to 11. P minus 1 is 10. So P minus 1 factorial is 10 factorial. What is 10 factorial? 1, 2, 3, product up to 10. So we know that for a prime number P, 1 and P minus 1 are self-invertible. That means 1 and 10 are self-invertible. So here, 1 and 10 are self-invertible. I can pair them, 1 and 10, I can pair them. 1 is this end and 10 is this end. But can we pair certain numbers? If you look at this 2 and 6. 2, 6, 12. 12 is 1 mod 11. Then 3 and 4 is 12. 3 4s are 12. Then 5 9s 45. 45 is 1 mod 11. Then 7 8s 56 is 1 mod 11. So I pair them like this. Once I pair them like this, then what happens? I get remainders 1, 1, 1, 1, 1. So finally I left out with the 10. 10 is congruent to minus 1 mod 11. 10 is congruent to minus 1 mod 11. So 10 factorial, that is P minus 1 factorial, is congruent to minus 1 mod P. That is your Wilson's theorem. The beautiful result, P minus 1 factorial is congruent to 1 mod P, your first classical theorem, Wilson's theorem. If P is a prime, then P minus 1 factorial is congruent to minus 1 mod P. The proof is same procedure what we have seen in the lemma. I skip the proof. Next I go to the Fermat's theorem, which is again useful for us. Before we go into the RSA, let me do that. Fermat's theorem. So the history of all this result, Fermat's theorem. The result is in the first proof of Fermat's theorem was given by Euler in 1736, the great mathematician Euler. So what is the theorem? Before going to the Fermat's theorem, again example. So this is how the interest comes in the topic. As I mentioned earlier, the proof techniques or the concept techniques varies for other subjects. For number theory, it comes out from the pattern or comes out to a problem, the result is generated. Let us take a number P, prime number 7. And another number not divisible by P, A equal to 12. So 7 does not divide 12. So there is the contradiction here. So let me take this A, 1 into A, 1 into A, 12. 12 is congruent to 5 mod 7. Fine. 2 into 12 is congruent to 3 mod 7. 3 into 12, 36. 1 mod 7. 4 into 12, 48. 6 mod 7. 5 into 12, 60. 4 mod 7. 6 into 12, 72. 2 mod 7. So I have tried 1 to 6. Took the product. I didn't try 0 because I want 1 to 6 here. 1, 2, 3, 4, 5, 6. Okay. So among these products, A, 1A, 2A, 3A, 4A, 5A, 6A. All this gives me residues. Look at the possibilities. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. These are the least residues. These are the least residues. When I take 1 into A, 2A, 3A, 4A, 5A, and 6A. But in some order, 1 into 12 give me 5, 2 into 12 gave me 3. So the order is 1 here, 2, then 3, 4, 5, 6. In some order, I'm getting this. This is very, very classic. So let us write it as a lemma. P is a prime, A is an integer, such that P does not divide A. Then the least residue of integer A, 2A, 3A, P, A, P minus 1, modulo P are permutation of the integers 1 to P minus 1. So the proof goes like this. So I'll take it granted that you can understand. Very, very beautiful, interesting proof. You can enjoy the proof really. It's understandable. What is the result now? I take the prime number and a number A, which P doesn't divide A, then A raised to the power P minus 1. So far we are doing adding multiplication. So now I'm raising to the power. What is the power? A raised to the power P minus 1 is congruent to 1 mod P. So this is the famous Fermat's little theorem. A raised to the power P minus 1 is congruent to 1 mod P. The proof is again using the residue, pairing the numbers. I'm A, 2A, 3A, P minus 1A, modulo P. I'm pairing. I'll get totally P minus 1 factorial. I parry 1, 2, 3 products as 1 and P minus 1, then 2 and middle term, all these things, and then I'll get the proof. So, not only that, the same example, I can say some more properties. Fine. So where it is useful? For problem side, for research side. So for encryption, for decryption, for cryptography, where it is useful. These are all tools. The classical results, Wilson's theorem, Fermat's theorem, and Euler's theorem yet to come. So as a mathematician, we are interested, okay, any problem? Yes, a remainder of 24 power 1947. When you divide by 7, what is the remainder? As you attack the base first, 24. 24 is 7 mod 17. Just next step, 24 reduces to 7. 7 raised to power 1947. By Fermat's little theorem, 7 power 16 is 1 mod 17. This is P. P minus 1 is 16. P minus 1 16. So 7 raised to the power P minus 1, 7 power 16 is 1. How many 7 power 16s are there? 121. 7 power 16 is there. Balance 7 power 11 is there. So I will split this 7 power 1947 as 7 power 16 into 121 plus 11. The 7 power 16 collapses to 1. Balance is 7 power 11. So one can calculate here onwards. Little bit rough and tough calculation. 11, 7 square 49 is minus 2. That is the catch for me. So for wherever 7 square comes, I replace it by minus 2. How many 7 power square is there? 7 power 10 plus 1 is 11. 7 power 10 becomes minus 2 power 5. Again and again I use the property. Again and again use the property, fundamental properties. I reduce it and simply comes out to be 14. 24 power 1947 reduces, the remainder is 14. Just in 5 steps. This is the beauty a mathematician will enjoy. Fine. Now comes the beautiful classical results, Euler's theorem. Before that, the Euler's phi function plays a major role in number theory. Not only number theory, it has application, excellent application in many fields. M is a positive integer. The Euler phi function, M, phi of M denotes the number of positive integers less than or equal to M and relatively prime to M. Catch this point carefully. Phi of M denotes the number of positive integers less than or equal to M and relatively prime to M. So how many positive integers are there which are less than M and relatively prime to M? So phi of 4 is 2. So 1 and 3, there are 2 numbers which are relatively prime to 4. What about phi of 9? Phi of 9, what are the numbers relatively prime to 9? Less than 9, 1. Yes, 2. 3 is not relatively prime. 4, 5, 6, no, 7, 8. That's all. So there are 6 numbers relatively prime to 9 less than. Phi of 4 is, phi of 12 is 4. Okay, there goes. So some problem, compute phi of 11. 11 is a prime number. So there comes the beautiful result. If you have a prime number, P, the value of phi of P is P minus 1. 11 is prime number. So 1 to 10, all the 10 numbers are relatively prime to 11. Phi of 18 is, we can find out the answer. Fine. So a small corollary, phi of P is P minus 1. So proof is very simple. I'll skip this. Now, we are going to see a property for a special property for this Euler's phi function. So I'll skip certain things. This is the Euler's theorem. What it says, if m is a positive integer, a is an integer, such that GCD of a and m is 1, then a power phi of m is congruent to 1 and m. You remember Fermat's little theorem, a power, when p does not divide a power p minus 1 is congruent to 1 mod p. Now, this is a special case. When m is prime, then a power phi of p is p minus 1. So, the special case of Euler's theorem is Fermat's theorem. So, this will be very useful for us. So, the proof technique is like using the residue modulo m. Okay, what are the possible residues? Means these are the numbers which are relatively prime to m. So, the proof technique goes in a lengthy way. So, I won't go into things. I'll skip those things, and these are some applications of problems and so on. So the main idea is multiplicative function. Phi is said to be a multiplicative function. What is a multiplicative function? Like in homomorphism in algebra, phi of x star y is equal to phi of x circle phi of y. Operation, the binary operation in G, binary operation H. Phi is a function homomorphism from a group G to group H. All these things we have studied homomorphism. Here in number theory, we have a certain function called number theory for multiplicative. This is the property. Phi of m into n is phi of m into phi of n. When m and n are relatively prime, that is most important. Take two numbers relatively prime, and phi of f of m n is f of n. This holds, then this particular function is multiplicative. A beautiful example is the constant function f of n is equal to 1. Or f g of n is equal to n power k. I can simply take f of 1 is 1 to 1, f of 1 into f of 1. These are some examples. So now we know the fundamental theorem of arithmetic. Okay, what is the fundamental theorem of arithmetic? When I take a composite number, I can write this canonical decomposition. So any composite numbers can be written as powers of products of powers of prime. Products of powers of prime in a unique way. So n is a composite number. I can split as p1 power e1, p2 power e2 up to pk power ek. This is called canonical decomposition. So let me do that canonical decomposition for a number and apply this multiplicative function. What happens? F of n. F of n is f of this p1 power e1, f of p2 power e2, f of p2 power ek. Not only this, I can split further. This is p1 e1 times it is repeated. So I can split for calculation. So this will yield a formula for calculating the phi of Euler's phi function. P is a prime and E is a positive integer. Then phi of P is P minus 1. What is phi of P power E? Phi of P power E is P power E minus P power E minus 1. So for the proof, I may take more time. So I will not go into the proof of this. The proof is 4 lines, but how to understand the proof is repeatedly telling the definition. Repeatedly telling the beautiful proof it is. Just 4 lines, but the proof comes not only by writing, repeatedly uttering the definition in the mouth. Like Tirukkural, if you say keep on telling, you get new ideas. The beautiful thing which we have, God has given for us for Tamil, Tirukkural. So likewise, look at the result, phi of P power E. It says the number of positive integers less than or equal to P power E is definition of phi function. Number of positive integers less than or equal to P power E and relatively prime to it. That's all. I have written all the definition. Next number equal to number of positive integers less than or equal to P power E. Remove minus number of integers not relatively prime to T. So if you are a subset, how do you remove? Identify you from the whole set, remove it, tell the balance people. Like that, among the numbers which are positive integers less than or equal to, remove this not relatively prime to. What is balance? Relatively prime to P. Phi of p power e is number of positive integers less than or equal to p power e and relatively prime to it. That is equal to number of positive integers less than or equal to p power e minus not relatively prime to p. So simple. Positive integers less than or equal to p power e not related to it is multiples of p. P, 2p, 3p, 4p, 5p. It goes like that. Till how much? P power e minus 1 into p. P power e minus 1 into p. And they are p power e minus 1 numbers. So from p power e, remove p power e minus 1 number. That is the formula. You cannot think a beautiful result like this. A formula comes out only by the definition. A formula comes out only by definition. That is a miracle. So phi of p power e is p power e minus p power e minus 1. Now we can compute the phi of any number. The phi of 8 is 2 cube. 2 cube minus 2 square. Answer is this. Phi of 81 is 3 power 4. 3 power 4 minus 3 power 5. So there comes. So a simple calculation. I remove this p power e outside. I'll get 1 minus 1 by p. This is beautiful again. P power e minus p power e minus p. Instead of that, p power e into 1 minus 1 by p. Where is my mobile? No, I want it someplace. They may call me. So like this we can extend. Like this we can extend. So on, right? So this is another property to show that this beautiful Euler's phi function is multiplicative. Phi of mn is equal to phi of m into phi of n. I'll skip this. All these things I'll skip, and then another beautiful formula. If I write canonical decomposition, then I can, using that previous formula, I can bring out a new formula n into 1 minus 1 by p1. All these things are done to make things simple. That's all. And again, this result is using multiplicative function by canonical decomposition. Each one becomes a formula, and the whole multiply out and then get the. And you can use this for computing phi function because it requires for us. Okay, my last PowerPoint is this one. Fine. So go back to my first today's start. Cryptography is a study of secret messages. For most of human history, cryptography was important primarily for military or diplomatic purpose. But internet commerce in the late 20th century made cryptography important for everyone. Anytime you send a text by something online or transfer funds electronically, cryptography is at work to guarantee, or so you hope, that nobody sees your information other than the intent recipient. That is the purpose. The most basic cryptographic protocols used today by millions worldwide without realizing it are based on number theory. So we have several sections here. Each section, what I'm going to use, and then that is I have narrated here. So to enter into RSA, because it's a very big procedure, the three people, Sir Vista, Samir, and Adleman, made this RSA system a tougher one. So how to pass the information secret, how to make it tough? As I mentioned earlier, if it is a linear, okay, I can find the inverse. If it is more than quadratic, cubic, what is the solution? Do you have integer solution? Do you have inverse, modular arithmetic inverse? That is the problem. So you make it tough. So how to prepare the composite number? Yes, I want to break it to canonical decomposition. Can you make it to 2 parts, a composite number? Why many parts? Very big number, you take a prime number. What is the largest prime? Still it's been searching. Oh, who is God? For a mathematician, the largest prime is the God. Can you see that largest prime number? Today one fellow will say, after 1 month or another fellow, okay, I found the next largest prime number. Find out the 2 largest prime numbers. Take 2 largest prime numbers, multiply them, prepare a composite number. Apply Euler's formula. The concept goes like this in the further. We will come to that as early as possible. I'll quickly go through the slides. It is based on exponential in modular arithmetic, and math began its Euclidean algorithm, Fermat's theorem, and primality test. All these things put together only we can make the system very, very strong encryption. Very, very strong encryption. Fine. In addition to cryptography, which aims to keep message secret from event droppers, there is a related called coding theory. I am not going into the coding theory basis other thing. Important in telephone networks and digital music, communication between NASA on Earth, satellite, space, number theory plays a role in coding theory. But in our discussion today, we will go back. Now look at back, you remember the Caesar and the Hell shapers, the movement of the letters which we had the earlier beginning, 3 the right side. Earlier I was doing 0 to 26. Now let me put 1 to 26 for the purpose of understanding here. This is the message that is doodle. It's encrypted as a GRR-GOH. What I'm doing is I'm shifting 3 plus to the right. What we did earlier, instead of 0 to 25, now 1 to 26. That's the difference. The encrypted message can be decrypted back. You know what is the procedure? Move left. What you move to the right side, you move right. This is very simple. The process by shifting fixed amount called Caesar cipher or shift cipher. Now we want to make it tough. What are the defects in this? Knowing the encryption process reveals the decrypting process. If we encrypt by shifting to the right by 5 letters, then the decryptor just shift 5 letters back and find out. Okay, how he will find out without giving the key? Key is private, but frequently occurring numbers are there. Very easy, 26 alphabets. Frequently something is appearing. If he gets one small clue, he'll decrypt it. Even if we don't know exact shift amount, the search space is very small because only 25 shifts is possible because it's a periodic. Modulo 26 is a periodic. So we know a message was encrypted by some Caesar cipher, then little enough maintenance for that to try for other cases. Because every letter is shifted the same amount, once we know encryption from one letter, we know the shift of all letters. Easily can break the clue. So what is happening here? I'll take A, 1, B, 2, and Z, 26. 3 letters, if you do encryption, the equation is X is equal to E of X. Encryption is encryption of X is equal to X plus 3 mod 26. Decrypted is D of Y is decryption is Y minus 3 mod 26. This is the reverse process. Fine. But what is the problem with this? What is the problem with this? Now, look at this. I have 2 O's here, O and O here. It becomes R and R here. Okay, but if first O is R, second O is also R, can I make this first O as R, second O as something? I'm making it tougher. I have to think of now apply number 3 here. Okay, we can get something a bit more complicated, allowing scaling before translation. E of X is equal to AX plus. This is linear mod 26. And this A and 26. Look at this. A linear LD has a solution if the GCD, a unique solution if GCD is 1 of A and M is 1. So this AX plus B is mod 26. This is Y is equal to, or some equation, this is some constant. Okay. So this is A comma 26 to be 1. The Caesar cipher uses A equal to 1. Then GCD of A need to be 1 in order to invert E of X. Otherwise, inverse will not exist. To decrypt the message, inverse should exist. If the inverse doesn't, so what is the inverse? I have to take A inverse. Suppose this is Y, then Y minus B by A is X. This is Y. Y minus B by A is X. So I want A inverse. Inverse should exist. That is the problem. Okay, fine. Let me go to the next slide. So let us take this E of X is equal to 9X plus 3 mod 26, an example. Then doodle becomes MHHGV. That you can check it. Descripting, you get the linear function. What is the linear? An ordinary, if you take ordinary an example, Y equal to 5X plus 3. Then what is X? Y minus 3 by 5. Y minus 3 by 5 is nothing but 1 by 5, inverse of 5. 1 by 5 into Y minus 3. This will work out in modulo. What is this inverse of, in a real number system, inverse of 5 is 1 by 5. It's valid. But here modulo, no ratio. We want an integer. 1 by 5, the inverse of 5. What is the inverse of 5? 21 is the inverse of 5 because 5 into 21 is 105. 105 modulo 26 is 1 here. So the inverse of 5 is 21 in modulo 26. So whenever I apply this 5x plus 3, the corresponding decryption function d of y is 1 by 5 is 21, y minus 3. So 21 y minus 21 into 3 minus 30 is the 63. Minus 63 is nothing but 15 mod 26. So the answer is 21 plus 8. Substitute values for y here, the ordinal number here, get back d of y and go for the inverse. That's all. That is simple. Okay, but still, this is not enough. Still, we have to make this tougher. This is linear. After all, linear relationship, we can break it. By allowing scaling mod 26 as a part of encryption, we can enlarge the encryption function more than 10 factors. Suppose x plus b, here it is 1 here, mod, it's very simple. If you make it the possibility of ax plus b, what are the possible ways you require to find the inverse? Again, it's simple. How it is only multiplying and adding. Earlier, I am adding p plus c, p plus k. Now I'm multiplying, making magnificent x and then adding. So again, it can be simplified because you know what is phi of 26 modem. How many possible ways we can find out this decrypting procedure? 26 ways you can apply for letters you can give for b number. For b you can carry from 1 to 26. Okay, then how many ways you can take a from 1 to 26 which are relatively prime to this 26 a relatively prime to 26, phi of 26. Phi of 26 is the number, Euler's phi function of 26 alphabets, numbers 1 to 26 relatively prime 26. So these many possibilities into these 26 points. So phi of 26 into 26. So 12, phi of 26 is 12 Euler's phi function. 12 into 26, 312 times. So this is breaking is very easy again. Even though the generalization, the Caesar cipher avoids problem, every letter is shifted to some amount. It shares the flaw that we did not bring up earlier. A letter gets encrypted in the same way, no matter wherever it appears in text. Fine. So look at this example doodle. Here x plus 3 I am taking, d becomes g, double times o, double times r. So there is a clue here that you have 2 times occurrence. So find the frequency. Mostly the letter E is frequently appearing in the English text. And then next common appearing letter is alphabet A. Once you catch this E and A, the rest of things the fellow will remove it from you. So therefore, if you have a long amount of encrypted text, we know it is encrypted by some function x plus b mod 26 could determine reasonably confidence which encrypted letters E and A. So again, we have to make further tough. So for that, what require? Further, we can prepare the Caesar cipher as a block cipher. What is a block cipher? I can prepare blocks of 2 by 2 matrices. For instance, doodle is my message. Break it to DOODLE. Fine. Okay. This I'll prepare DO. What is the ordinal number of D4? Ordinal number of O 15. A is 1, B is 2, C is 3, D is 4. Not like previous case 0 to 25. It is 1 to 26 is 1, 2, 3 up to 25. 26 is made 0. Z is made 0. Okay. So here DO is 415. Next OD. OD is it's a column vector. Then LE 1215. I'll take a matrix randomly which has inverse exists. So A is equal to 3, 2, 1, 11. All numbers below 26. So I have a matrix 2 by 2 matrix and I have a column vector here. Look at this. What is happening? To encrypt the block of 2 letters as a vector of 2 components, I am multiplying this A into the first DO. Answer 16, 13. Multiply the matrix 2 by 2 with 15, 4. A into 12, 5. I have the new column vectors are there. This is encrypted. Turning each vector component back on the letter, this doodle first letter P is equal to 16. This is P is 16. M is 13. Okay, like so 16, 13, then 1, 7, A and G, and then 20, 15, T and O. So PMA GTO. So doodle has become PMA. So there is no repetition. Look at this earlier in my linear way of combination AX plus B. Doodle, 2 O's were there, 2 D's were there. 2 D's going to same number G, 2 O going to RR. Now that problem is solved. Look at here. PMA GTO. D is going to P, this D is going to G. The first O is going to A, and second O is going to, first O is going to M, second O is going to A. So there is no there's no clue here because I'm making block shipper. I have tightened the security now. Once I do this, then I notice that this not repetition is there. And then though it would be susceptible to analysis based on frequency, it's not possible, double letter combination in English. And now the decryption, suppose we received the message, how to decrypt it. Suppose a new message, we get it from the opponent side. We take this clue that A matrix and then affect the inverse of the matrix. What is inverse of 2 by 2 matrix? Yes, 1 by determinant of A, D and A is change the position minus it is into product. So encryption is A into V, vector column vector. Decryption is A inverse into V. There is beautiful inverse matrix inverse exists, 2 by 2 matrix, invertible matrix, A inverse V. Fine. So with that, I will take this matrix and then do this procedure, write the determinant, apply it, and take back my inverse process. So this is a beautiful result 2 by 2 matrix in this integer model of modem, and gives the result. Fine. Okay, but some toughness is there. We have given some toughness, and again we go back in the reverse process. The inverse is fine. With this, we can also extend to 3 by 3 encryption messages. Fine. But what is the next stage? The encrypted matrix for a hill shipper can compute its inverse using a row reduction or method of linear algebra. For the German Enigma mission, the figure was cracking by allies was one of the greatest achievements in World War II. Encryption decryption were literally the same steps. Okay, and this is the defect the mission. Again, in 1970, okay, it was discovered that it could otherwise their cryptographic algorithm based on number theory, where the encryption process can be announced to the whole world and decryption is still secure. Okay, I throw you the key in the Bay of Bengal, go search it. I throw the key in Arabian Sea, go search it. I am having the yes, it's public key. I throw it challenging you that can you open the door. That is public system. So RSA was one of the first practical implementation of this idea based on encryption, the power function in modular. So the highest thing is exponential. Today the pandemic situation, we are not able to predict, we are not able to put in a pattern, any progression, arithmetic, geometry. Nothing is possible. The virus is growing, the COVID-19. So this is going in exponential curve, we say. X power E. Come on. It was possible translation. Yes, we can break the code. If you take it in terms of what is a linear X plus B, code is broken. If you take it in matrix, yeah, still it's possible to crack. So go for the modular arithmetic power function X power E modem. So decryption is also power function Y power D modem for some modulus M another exponent D. When we learn how RSA works, we will see the figure out the decryption exponent becomes very difficult of factoring. So what is this behind this? This is the Enigma mission of the that was also. So let us see an example. A cube is 14 mod 55. The possible solutions are 0 to 54. Keep on give for A various values. We can find out the solution. It's invertible. 14 is invertible model of I. Okay. So here comes the classical results. When I want to solve A power n mod 40 mod of 55, what is phi of 55? So Euler's phi function phi of 55. Phi of 55, it's a 55 is 5 into 11 by multiplicative function phi of 5 into phi of 11, prime number 5 and 11, answer is 40. So I can write A power n 40t is A power n, A power 40 power t is going to be A power n. So this is what the catch here. A power n plus 40t is congruent to A power n 40. So A power 40 is 1 mod phi by Euler's theorem. You know very well A power phi of p is congruent to 1 mod m. Euler's theorem in the previous PowerPoint, I made a statement. A power phi of m is congruent to 1 mod m. Okay, that is Euler's theorem. And A and m GCD is 1. So that is the application of Euler's theorem here. So I can take this equation and frame the equation, raise to the power both the sides raised to the power k, and then I solve this using Euler's algorithm. GCD of 3 and 40 is 1. I trace back it to find the inverse. 27 is the inverse. Okay, fine. So in this way, I formed a solution that for A is equal to the 9. 9 cube is 729. That is equal to 14 mod 15. So we get crucially the exponent of 3 relatively prime 40 and so on. So this is one technique here. How to insert your start with the RSA. So actually, what is happening in RSA? What are things required? I require 2 prime numbers. 2 different prime numbers P and Q. I want to take the product. I prepare a composite number M. What is phi of M? Phi of M is phi of P into phi of Q. P minus 1 Q. The answer is ready. I know phi of M. I know this is private. P and Q is private. I will throw this large number public. I will throw it to the public. But this is God for me. I want largest prime. As a mathematician, we will say numbers are God for everybody. Everyone is attached with a unique number called Aadhaar number. So everyone has a number for us. So for a mathematician, still he finds the largest prime mostly for us. So once you find the largest prime number, you are seeing the God. So I want big 2 prime numbers. Prepare this composite number. The second ingredient is what? An integer e such that e and phi of m is 1. What a horrible situation. You see that very, very difficult. Find a number e such that it's relatively prime to phi of m. Phi of m is nothing but phi of pq, that is equal to q minus 1 to q minus 1. So by an exponent encryption, this will encryption exponent to verify. You could use Euler algorithm. All these things are fundamental. So you prepare. The third ingredient is that multiply ed, that should be equal to 1. The inverse d is the inverse of e under modulo phi of m. So you just start. You just give this data. M and E are your public key. A prime is P and Q, which is your private key. With this, you message to be sent to, okay, as an integer. You want to send an integer as a message. Okay, the long message can be broken into blocks less than m, and then someone who wants to pass along your message x, the instead send an encrypted message e of s would XOR e mod m. The decryptor will receive the message. If he knows the technique, what he has to do is he has to decrypt it as y power d mod m. There is a problem. Choose a simple case of 43 and 97. PQ, calculate phi of m, 4032. 5 is relatively e is your 5, and we make the equation. We encrypt it, use this procedure, XOR phi mod m. The decryptor will find the D. The D is E is given to him. We find the inverse. Inverse of D is 1613. After that, you used to apply here and put the ordinal numbers and find out this. So finding this D, finding without this P and Q, breaking this into canonical down portion of 2 prime factors, because they are not easily small prime numbers, they are largest prime numbers. How to go and find out the prime divisor. Once you find the P, then you can find the Q. So there is the difficulty in this study. So in that way, this is the result. Xe x power d is congruent x mod m, and so on. So this, I think, with this input, maybe the summary of the RSA system. There's some examples are given. How it works out. The information is taken, and then it is made a number, and so on. Another example. This is another example. I have crossed the 11 time. These are some problems, heavy problems, but I feel that the day will be successful for all of us if at least you feel the flavor of number 3 and the importance and how we, where are we. See, I am not a number theorist, to be honest. I am a graph theory person, worked in graph labeling and automata theory and little chemistry and graph theory. After my interest, I had a chance, I will work in number theory. I thought of studying complex analysis. I didn't get a chance. I thought of studying number theory, get a chance. Whatever chance I missed it, I'm studying. It's a never-ending process. Studying is a never-ending process. Till the end of the life, we have to keep reading, okay, and listening to the environment, and we should, sincere in learning, sincere learning. So this is the history of RSA. What happened in 1977, and then later stages, how it went in 1997, years after the original or discovered RSA. Still, it's God for us, finding the largest prime. These are the references. Coke, a note on non-secret encryption, 1973. These are all available internet. You can, plenty of data is there internet. Even I used to learn. This is the paper, 1978. It's available online. Revist RSA, method of digital, and Weiner, RSA secret exponential. This is. So once again, I thank the organizers of SRM Maths Department, the HOD, Bapuji, and all the people who are involved, and also the faculty members to patiently listening in this time 4 to 6. Okay. Thank you very much, sir. Thank you, one and all the best.
Sir, thank you, sir, for your wonderful lecture.
Okay.
So you mentioned about linear Diophantine equation, and you were using only the positive x and y in finding the solution. Any particular reason for omitting negative solutions?
No, negative solutions are also existing, sir. Actually, the straight line when you draw, but we are see actually for the purpose of this LD application is to find the positive solution.
Okay.
But when you want integer solution, negative is also allowed. I have taken my examples to positive. That's why I talked about positive. Otherwise, negative side is also line is extended. You have integers. We want integer solutions, not only positive. Diophantine means you have integer solution, not only positive, both positive and negative. In our example, the case was fruits and coconuts, so it was positive.
So you want to take only integer values?
Yes, sir, integer only. Then only it is called Diophantine equation. That is it.
Okay. And similarly, the geometrically, if you think the points are lying on the straight line, similarly, if you consider a circle, there is a symmetry always there. Can you correlate the set of points x comma y with the Diophantine? Is it possible?
Actually, it's the idea of Diophantine started from the Pythagoras concept, right angle triangles. Right angle triangle, the sum of squares of two sides is equal to square of third side. We can draw infinite number of triples, triangles, right angle triangle. But the interest is we want only integer values, not real values. So there it started the concept, and then Pythagoras triples, and also the Fermat's theorem, a square plus b square is equal to c square. A power n plus b power n is c power n. A cube plus b cube is equal to c cube. So generally is x power n plus y power n is equal to z power n. All these things are idea. But as you mentioned here, in a cycle, there's no length concept, no? So that way it's I don't think so. It is possible.
Okay.
Yeah, again to your knowledge, all of us are learning. I am not a researcher in number theory. To my knowledge, I'm answering to you. Go ahead, sir.
Okay. Thank you, sir. Thank you. Any questions from the audience?
Yes.
Sir, good evening.
Good evening, sir.
I am Ganesh Kumar from Computer Science Department.
Yeah, Ganesh. Yes, Ganesh Kumar.
How are you, sir? Fine, sir.
Fine, thank you.
How you are the number theory with implemented in blockchain technology, sir? Any number theory concept implemented in blockchain technology nowadays?
Sir, are you watching the slide? Are you watching the slide?
Yes, sir. Yes.
Yeah. I have given encryption, decryption. I don't have time. So in the screen, in the PPT, you have the proposed system using modulo arithmetic 3 and complete graphs. Yes, what you asked is I can encrypt a PIN number, a password, or an ID, whatever it is officially, a number which is divisible by 3, or PIN number, or a secret code number which is not divisible by 3. For both the cases, I have prepared one of my research scholars myself. We have taken a complete graph. We split the numbers into 3 parts: residue 0, residue 1, residue 2, and put it in the graph along with the graph labels. And then in that one triangle, 3 points are required for one triangle. One triangle will carry the key. Rest of the NC3 triangles will not carry the key. It will not be the solution. That if you identify that one particular triangle, then easily you can take the number. You can see the screen that the triangle is a red color. And then from that we do the decrypt and calculation. The calculation says that it is the formula n equal to sigma 3 into f of uv plus f of v. If I do this, I can get back the number, which pin number which you encrypt. The decryptor will know. It's a beautiful work which we have done myself and research scholar, implementing in a labeled graph the encryption techniques.
Yes, sir. Yes, sir.
Thank you.
Okay, thank you, sir.
Thank you.
Any other question from the audience?
Hello.
Hello,
Yes,
sir.
Professor. Yes, Professor.
Hello.
Please, Professor Ganeshans.
Yes, yes. This is Ganesan. So
Yes, sir.
Babujee.
Yes, sir. Yes, sir. Fine, thank you.
Yes, sir. Yeah. Congratulations for your nice lecture.
Thank you, sir. Thank you, sir.
Okay.
Thank you, sir.
Thank you.
so
Thank
much,
you
sir.
for your nice.
Any other question? Audience, if you have any particular question, please ask. People who are taking a number theory, people who are working in number theory, people from computer science, if you have any difficulty, please ask.
Yeah, the good book which you can refer easily is Thomas Cauchy. Introduction to Number Theory by Thomas Cauchy. It's a very big book, good book for us to learners. Thomas Cauchy, especially for computer science people, very useful book it is. Yeah, any questions? I'm waiting to answer.
Any questions from the audience? So just got application in computer science, the field of IT industry, also
Yes,
in
sir.
all the science and technologies.
Yeah.
Yes, sir. Yes, sir.
Any question would you like to ask? Because professor is waiting for us.
Share it full screen.
Okay, if there are no questions, shall we conclude? If there are no questions, we have to conclude.
Yes, sir.
Okay.
Yes, sir. Conclude, sir.
Okay. So, Professor, actually, I want to say a few things. Nowadays, we are going to teach through online.
Yes.
Sir has set a role model to us today. He has taken 2 hours lecture. See the voice modulation. We have to learn from him. If we are going to teach mathematics through online, you have to make students alert. Usually, students will do some mischievous things. But I think if you follow like our professor, I think you can have the attention of all our students. So it is also the capacity of the teacher to make the students alert and listen to your class. Today, you see, he has given a lecture for 2 hours. What was how interested he was? I was actually noticing him from the beginning. Even though it was 2 hours, he was having interest. He was very much interested to give the lecture, and the voice modulation and the way he pronounces, it was very nice. I think students also expect such things. Am I right, Professor?
Yes, sure, sir. All this encouraged by the audience also. Nice. Anyhow, we have to be very alert, sir. This time, when you take online classes, we have to imagine that all the students are before us. The imagination is more important. One of the preparation mode is even imagining what the students mood, how to make them alertly listening us. That is important, sir. Sure.
And also given a nice tips. You have to give examples, even though the theorem is proved already. Give example. Try to give the results so that you can see where the case fails. So by the way, I think you can draw the attention of our students. So I think the faculty members who are attending today will have a better way of taking online classes, I suppose. Also, generally, when we allot workload, people are not interested to take number theory. Today, I given a nice presentation, and it has definitely motivated our staff members, sir. And I think people will be interested to take number theory after. That is my assumption. So I thank Professor Baskar Babujee for giving excellent, thought-provoking and motivating lecture. So on the behalf of our maths department and the people who are listening through online, I am very grateful to our professor. Thank you for accepting our invitation in short notice. You have made us thrilled actually by your way of lecture, sir. Actually, when you are given a chalk and board, we are very familiar to do things on the board. But in online, you are doing well, sir. Your online students are grateful to you, and they are very lucky to have you as a professor, sir. I'm very happy about this lecture today, sir.
Yes.
So I thank our professor for giving a valuable lecture, and I thank all the audience for patience hearing. And day 2 is successfully completed.
Okay.
So anything else? And today you have circulated the feedback form, so you can fill the feedback form, and any queries are there, you can ready to answer. Okay. So anything else, Babujee? Babujee Pullepu?
Nothing, sir.
So thank you, Professor. Thank you for joining with us. Thank you for giving
Thank
lecture
you,
to
sir.
us. Thank you.
Thanks a lot, sir.
Thanks.
Babujee, sir.
Okay, sir.
Thank you, sir. Bye. Bye, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank
Bye,
you,
sir.
sir.
Thank you, Professor.
Thank you to all, Babuji. Thank you.
Thank you. Okay, Babuji, you can end the lecture. You can
Yes, sir.
end the meeting. End the meeting. End the meeting.
Yes. Sir, kindly fill the fastly. Actually, they need another meeting. They are connecting within 10 minutes. Those are completed this week and those not completed, do the fasting feedback. We are ending the meeting within 10 minutes.
பாபுஜி சார் நான் லாக் அவுட் பண்ணிக்கிறேன்.
Sivan, you column, sir. Post all of you, if you complete, you can leave, sir. Thanks.
Okay, Babu.
Thank you sir.
Thank you,
Sir,
Sivan.
நான் கூட ஆதித்தன் நான் கூட லீவ் பண்ணிக்கிறேன் சார்.
புரியல.
ஓகே சார். Thank you. ஆதித்தன் நான் லீவ் பண்ணி லீவ் மீட்டிங் கொடுத்துடலாம் இல்லையா?
லீவ் பண்ணுங்க. எந்த மீட்டிங் வேண்டாம், you can leave.
ஓகே. Thank you.
Okay, sir. Bye.
Okay.
Nani Baba.
Okay, sir. Vegetation, column.
Okay. Bye.
Vijay.
Okay, sir. Okay. Another meeting, sir.
இருக்கு இப்ப 7 அங்க ஒரு பிசிக்ஸ் மீட்டிங் கேட்டாங்க. 6:30 ஸ்டார்ட் பண்ணுவாங்க அவங்க.
Okay, sir. Okay.
அவங்க ஆல்ரெடி வெயிட்டிங்ல இருக்காங்க. ஃபோன் வந்துட்டாங்க. சஞ்சீத் குமார் ஃபோன் பண்ணு சார்.
Hi, sir. Okay.
நீ போலாம் விஜி.
Okay, sir.
நான் வெயிட் பண்ண கொஞ்ச நேரம். ஷோபனா மேம் முடிச்சா நீங்க போலாம்.
சார் நான் அதை இப்பதான் ஃபில் பண்றேன்.
Thank you, ma'am.
ஓகே சார்.
Sir, Babuji, sir. Good evening. Sir, this is Ramesh from Vadapalli campus, sir.
I know, sir. Tell me, sir.
Sir, the feedback form not able to submit the last one, sir.
என்ன கதரா?
The feedback form, sir.
என்ன இருக்கு?
லாஸ்ட்ல அந்த இது டிஸ்ப்ளே ஆக மாட்டேங்குது. அது
சப்மிட்டா? ஏதாவது கொடுத்தீங்க மேல?
Babuji sir, தளபதி எனக்கு சேம் ப்ராப்ளம். சப்மிட் பண்ண முடியல.
எல்லாம் ஃபில் பண்ண முடியுது, ஆனா வந்து சப்மிட் பண்ண முடியல சார்.
மெயில்ல லாகின் பண்ணுங்களே. லாகின் பண்ணா வரும்.
சார் ரிப்பீட் பண்ணுங்க.
லாகின் பண்ணா வரும்னு நினைக்கிறேன் சார். த்ரூ லாகின். டைரக்டா ஓபன் ஆகாது.
எஸ் சார், மெயில் ஐடி லாகின் பண்ணா தான் வரும். தளபதிஜி
எஸ் இருங்க, மறுபடியும் போயிட்டு வரேன்.
நீங்க மெயில் ஐடி கொடுத்து லாகின் போங்க, வரும்.
ஓகே thank you. ஓகே பாலகணேசன்.
Babuji sir, I am leaving.
Okay, thank you madam. Thanks a lot.
Bye.
Bye ma'am.
மெயில் ஐடி போய் பண்ணணுமா சார்?
ஏதோ ஒரு மெயில் ஐடில லாகின் பண்ணுங்க கூகுள்.
ஓகே.
இல்ல நீங்க SRPST லாகின் பண்ணுங்களா? I'm closing. I hope all of you completed.
சார் நான் கம்ப்ளீட் பண்ணல சார். I am doing now.
Yes.
Babuji sir, I am doing now.
Hey, ID வேணுமா?
Babu sir. Babu sir.
சொல்லப்பா. சபரி.
Submit வரல ஜி. Submit வரல.
Submit எல்லாம் விட்டுடு. ஒன்னும் வர போறது இல்ல வெச்சி.
சரி நீங்க சொல்லிட்டே போதும். சரி ஓகே. ட்ரை பண்றேன் இருங்க.
லாகின் மெயில் லாகின் பண்ணப்பா.
லாகின் பண்ணிட்டே போனேன்.
போட்டுடு. நீ வரல ஆப்ஷன் போடுற நீங்க.
அப்படியே இருங்க வேணா நான் போன் பண்றேன்.
ஹலோ. சொல்லுங்க மேம். லாகின் பண்ணிப்பா மேடம். லாகின் பண்ணாதான் மேடம் மெயில் லாகின் பண்ணாதான். சரி நீ நான் இங்க இப்போ இன்னும் அதுலதான் இருக்கு. இப்போ 10 மினிட்ஸ்ல மூடிட்டு போறேன். ஏன்னா மெயில்ல போட முடியல. இல்ல உங்களுக்கு நான் தப்புல போடுறேன். பாருங்க கேளுங்க என்ன செப்பரேட்டா மெசேஜ் அனுப்புங்க நீங்க. இல்ல வரலங்க. சரி ஓகே. Sir, all of you, I am closing, ending the meeting, sir, because they have other meeting. Yes. Sabri, சொல்லு Sabri.
கம்ப்ளீட் பண்ணல லாகின் பண்ணி நிக்கிறேன். ஒரே நிமிஷம் இருங்க.
இல்ல நீ browserல ஓபன் பண்ணா நான் இங்க வரணும்னு அவசியம் கிடையாது. நீ browserல ஓபன் பண்ணு. நெட்ல ஓபன் பண்ணி இந்த மீட்டிங் அதுக்கு சம்பந்தமே இல்ல.
சரி அப்படினா ஓகே பை.
நீயே கூட வெளிய போலாம்.
ஓகே